So we've derived the FLRW metric, which is the spacetime metric that describes an expanding universe, and we've also derived the various tensors related to the FLRW metric. In this video, we're going to calculate the paths of free particles in an expanding universe, and these paths are the FLRW geodesics. This will also lead us to discussing comoving coordinates. We'll also talk about cosmological redshift of light in an expanding universe and cosmological horizons. So in this video, we'd like to figure out how all the galaxies in the universe spread out over time as the universe changes size according to the scale factor A of t. We'll figure this out by looking at the spacetime geodesics in the FLRW metric. Recall, a geodesic is the path a particle takes through spacetime when it has no forces acting on it, and is only affected by the curvature of spacetime. These geodesic paths are given to us by the geodesic equation, which contains the connection coefficients. In the last video, we found that there were 13 independent non-zero connection coefficients for the FLRW metric. Because there are so many connection coefficients, solving for a general geodesic using the geodesic equation will be difficult. But what we can do instead is guess a special case for a geodesic and then check that it works. Our special case for our geodesic will be paths with constant space coordinates that move along the time coordinate curves. So let's take some initial spacetime point called B, and B will have coordinates for time r, theta, and phi. Now let's travel along the direction of the time coordinate using the path parameter lambda. So we'll add lambda to the initial time coordinate and leave the space coordinates the same for all time. So these coordinates describe our space-time world line. The derivative of time with respect to lambda is 1, and the derivatives of the space variables all go to 0, since they're all constant. And all the second derivatives go to 0. Given this, our geodesic equation becomes very simple. All the second derivatives go to 0, and the only first derivatives that are non-zero are the time component derivatives. So we have connection coefficients with lower TT indices. And since these derivatives equal 1, the geodesic equation becomes these coefficients equaling 0. Rewriting the lower t indices as 0 indices, if we look at our list of all the non-zero FLRW connection coefficients, we don't find any with 2 lower 0 indices. This means these coefficients are 0. So our geodesic equation becomes 0 equals 0, meaning the geodesic equation is correctly satisfied. So since our original guess of world line satisfies the geodesic equation, these world lines with constant space coordinates are geodesics in the FLRW spacetime. So what we found here is that if a free particle travels through spacetime with constant space coordinates, it will continue to have constant space coordinates for all time, as long as no non-gravitational forces act on it. Another way to think about this is to say that the FLRW spatial coordinate grid will expand along with the universe when the universe expands, and contract along with the universe when the universe contracts. For this reason, FLRW coordinates are called comoving coordinates, because the spatial coordinate grid changes size along with the universe. Now, you might argue that if two particles have constant space coordinates, the distance between them isn't changing. But remember, we can't trust our eyes when it comes to spacetime diagrams. Spacetime coordinates don't have any direct physical meaning. We should instead calculate the proper length between these 2 points. Let's take one particle at the origin of our coordinate system, and another particle at a radial distance of r equals d, with 0 angular coordinates. In an expanding universe, according to our FLRW geodesics, If these particles start traveling with constant spatial coordinates, they will maintain the same spatial coordinates for all time, and so their coordinate separation will be d for all time. However, to get the true physical separation between these two particles, we need to draw a path between the particles at a constant time and integrate over the path to get its proper length L0. We can parameterize this path using a path parameter lambda, but since this is a path along an r coordinate line, we can just use r as the path parameter. To integrate over the length of the r tangent vectors, we use the square root of the negative dot product, since these are space-like tangent vectors with a negative squared length. The dot product of the r basis vector with itself is just the metric component grr, which is negative a of t squared over 1 minus kr squared. Canceling the minus signs and pulling the a of t function out of the integral, since it does not depend on r, we get this integral formula for proper length. For a flat universe with k equals 0, the square root term in the integral just becomes 1, so the proper length is just the scaling factor times the r coordinate. For a closed universe with k equals plus 1, this integral gives inverse sine of r. And for an open universe with k equals negative 1, this integral gives inverse hyperbolic sine of r. So regardless of the universe's spatial shape, the scaling function a of t really does change the physical length of the r coordinate over time. And so the distance between two free particles really does change over time when the FLRW metric has a changing scale factor. So we've calculated the geodesics for massive particles in a universe that changes in spatial scale according to the FLRW metric. But what about the geodesics of massless light beams in a universe with changing spatial scale? We know that for light-like world lines, the tangent vectors are light-like vectors, with a squared length of 0. So if we look at a radial light beam in FLRW spacetime that's traveling in the r direction with constant theta and phi coordinates, the formula for the squared length of the tangent vector looks like this, which we set to 0 for a light beam. After distributing over the dot product and plugging in the metric components, we get this equation. And since we can set the path parameter to anything we want, let's use lambda equals r. So this goes to 1. And if we take the reciprocal of both sides, we get this. This differential equation gives us the slope of light beams according to their r and ct coordinates in FLRW spacetime. And this is really 3 different formulas for closed, flat, and open universes. Now, for simplicity, I'm only going to consider the flat k equals 0 case for the rest of this video. Most current evidence indicates that the universe is very close to being flat, so this is the case most relevant for our universe. If we take a scale factor of a equals 1, then the light beams will have a slope of 1, as expected in a flat spacetime according to Cartesian coordinates. For a scale of a equals 2, the slope of light becomes 1/2. And since time is on the vertical axis, this means the slope is more vertical. For a scale of a equals 3, the slope is 1/3. And for a scale of 1/2, the slope is 1/1/2 or 2. So it almost looks like light travels slower in large-scale universes and light travels faster in small-scale universes. But that's not true. The local speed of light, measured as the ratio of proper length over proper time, is always equal to c, or a slope of 1 if we treat c times tau as proper time measured in units of distance. These derivatives in front of us are just the coordinate speeds, and so they are allowed to change. When the scale of the universe is 2, each coordinate grid box really represents 2 units of distance according to the metric. So light going along at the usual constant speed only crosses half of one coordinate grid box per unit time. When the scale is 3, a coordinate grid box represents 3 units of distance. So light going at the usual constant speed only crosses 1/3 of it. And at a scale of 1/2, each grid box represents 1/2 units of distance. So light at the usual constant speed crosses 2 grid boxes. So the local speed of light is not changing. It's just that the coordinate grid boxes are changing physical length over time. So the ratio of the time and space coordinates for the speed of light also changes over time. Now, without a specific scaling function a of t, we cannot solve this differential equation. The best we can do is to look at these slope diagrams. However, if you recall the concept of a light wave covector field, which we used to draw light waves in Schwarzschild spacetime in Relativity 108e, we can write out the form of the light wave covector field in FLRW spacetime like this. Now let's use this formula to understand cosmological redshift. So looking at this formula, something very important to notice is that the derivative dr by dct depends only on the time variable through the scaling function a of t. There is no r dependence here. This means that at any given time t, all beams of light in the universe will have the exact same coordinate speed dr by dct. This means that, when looking at a light wave, each peak of the light wave will be traveling at the exact same coordinate speed, because the coordinate speed doesn't depend on position. At a scale of a equals 1, both peaks travel with a coordinate speed of 1. At a scale of a equals 15, the coordinate speed is modified by division by 15 for both peaks. And at a scale of a equals 1000, the coordinate speed changes with a factor of 1/1000 for both peaks. So, since these two peaks are always traveling with each other at the same coordinate speed, the conclusion is that the coordinate distance between the two peaks, delta r, never changes. Now, even though the coordinate distance delta r between wave peaks remains constant, the actual physical distance, or proper distance, between peaks is changing over time along with the scale factor. So for a scale factor of 1, the delta r corresponds to this proper length. At a scale value of 15, the same constant delta r coordinate distance corresponds to the original proper length times 15. And at a scale value of 1000, the same constant delta r coordinate distance corresponds to the original proper length times 1000. So even if the true physical distance between wave peaks can change over time, the coordinate distance delta r between wave peaks remains constant for all time. Another way of interpreting this is that the distance between wave peaks will expand along with the universe, or contract along with the universe if the universe shrinks. So in a universe with a changing spatial scale a of t, a constant comoving coordinate distance delta r corresponds to a changing proper length. So the physical distance between peaks in a wave is the same thing as the wave's wavelength, lambda. So if this proper distance changes with the universe's scale, the wavelength of light will also change with the universe's scale. So let's say a galaxy emits light at a time t emit, when the universe has the scale a of t emit. And later, the light is then received by Earth at time t receive, when the universe has the scale a of t receive. How can we determine the change in the light's wavelength due to the change in the universe's scale? Recall, the coordinate distance between the wave peaks of light, delta r, is constant for all time. At the time of emission, the wavelength, which is the physical distance between peaks, is just delta r times the scale factor at the time of emission. And later, at the time of receiving the light, the wavelength is the same coordinate distance delta r times the scale factor at the time of receiving. If we take the ratio of the two wavelengths, the delta r's will cancel in both formulas since the coordinate distance between wave peaks never changes. So the ratio of wavelengths at the time of emission and the time of receiving only depends on the ratio of the universe's scale at the time of emission and the time of receiving. So the universe's expansion or contraction can change the wavelength of a light beam. And since wavelength is inversely proportional to frequency, we can get a similar formula for the frequency of light, just with the receive and emit terms flipped. Also, in some texts, you'll see the time of emission labeled t then for the past, and the time of receiving as t now for the present. This is the formula for cosmological frequency shift, which keeps track of how the frequency of light changes due to the expansion or contraction of the universe. This ratio is sometimes written as 1 plus z. Z equals 0 means the emitted and received frequencies are equal, and no frequency shift happens. Positive Z means the emitted frequency is larger than the received frequency, indicating redshift happens. This happens in an expanding universe, where the scale factor grows over time. A negative Z means the emitted frequency is smaller than the received frequency, indicating blue shift happened. This happens in a contracting universe where the scale factor shrinks. So the idea that wavelengths of light expand or contract with the universe makes intuitive sense, but I want to bring up one technical detail. Remember that a particle has no objective x momentum. Different observers will measure different x momentum values depending on their reference frame and the direction of their x-axis. Similarly, a light wave has no objective frequency. Different observers will measure different frequencies depending on their reference frame. So when we're talking about light redshifting or blue shifting due to the expansion of the universe, which reference frames are we measuring in? This formula only works for comoving observers that are traveling exactly on the time coordinate curves in our FLRW coordinate system. If any of these observers are wiggling back and forth relative to the comoving coordinates, we'll need to take into account an additional Doppler effect on top of cosmological redshift or blue shift when calculating our frequency shift. This time coordinate in the FLRW coordinates corresponds to a special reference frame called the cosmic rest frame. Loosely speaking, the cosmic rest frame is a global frame for the universe where the average momentum of all objects at the largest scales is 0. I'll talk more about the exact definition of the cosmic rest frame in the next video, Relativity 110e. One last question I'll try to answer is, do we expand along with the universe? We've learned that free particles will all move apart from each other in FLRW spacetime with an increasing scale factor. This indicates that all the galaxies in the universe are moving apart from one another. We've also learned that the wave peaks in light waves will expand apart from each other in an expanding universe, leading to cosmological redshift. So some natural questions to ask are, do atoms, people, star systems, and individual galaxies also expand along with the universe? Answering this correctly is a bit tricky, but I'll do my best. The first thing to note is that the individual particles that make up atoms and everyday objects, like cars and people, are not free particles. They are bound together by forces like the electromagnetic force or the strong nuclear force. The expansion of the universe is incredibly weak compared to these forces, so it can basically be ignored in the case of atoms and everyday objects. Now, when it comes to star systems and individual galaxies, the individual objects inside these systems are essentially free particles. only affected by the curvature of space-time and no other forces. But objects in these systems do not expand along with the universe either. The FLRW metric that is used to describe the expansion of the universe came from the assumption that the universe is homogeneous and isotropic. But on the scale of individual star systems and galaxies, the universe is not homogeneous and isotropic, so the FLRW metric does not apply. These systems tend to involve several smaller bodies orbiting around a more massive body, with a lot of empty space in between. These systems are better described by something closer to the Schwarzschild metric, so FLRW-style expansion does not apply at the scales of individual star systems and galaxies. That said, we are ignoring one important detail. In Relativity 110F, I'll talk about a form of dark energy called the cosmological constant, denoted by capital lambda, and how it causes the universe's expansion to accelerate outward. The true Schwarzschild metric that we derived in Relativity 108A involved the assumption of a zero cosmological constant, and the Einstein field equations reduced to the Ricci tensor being zero. In a universe with a non-zero cosmological constant, the vacuum solution for a spherical body will be slightly different than the Schwarzschild solution, since the cosmological constant will act as a source of spacetime curvature on the right-hand side. One example metric solution is the de Sitter-Schwarzschild metric, which describes a black hole in an empty universe with positive cosmological constant. I'm not going to derive this metric solution. Instead, I'll show a loose approximation of what Newtonian gravity would look like if it had a cosmological constant, and draw some conclusions from that. The Newtonian equivalent of the Einstein field equations is Poisson's equation. So let's include a cosmological constant term in Poisson's equation and see what happens. I'm using a plus sign here since that's what's required to produce an outward repulsive force, and I'm including a factor of c squared to get the units right. If we insert a point like mass density and solve for the potential, then compute the force by taking the gradient and multiplying by mass, we get the standard Newtonian gravity force term plus this additional term, with an opposite sign. So the cosmological constant provides a kind of repulsive force that increases linearly with distance. But this force is incredibly weak because the cosmological constant is incredibly tiny. This term only becomes significant at huge distances on the scale of galaxy cluster filaments. But technically speaking, this repulsive force is non-zero even at small scales. And compared to a universe with a zero cosmological constant, this small non-zero force would slightly increase the default size of gravitational systems like star systems and individual galaxies. But this slight increase has already happened, and this won't tear gravitationally bound systems apart in the future. Now, I'm going to go a little outside the knowledge I feel I confidently understand, but I'm going to quickly mention the Big Rip. Some popular physics sources talk about a possible future of the universe called the Big Rip, in which all galaxies and atoms are eventually torn apart by the expansion of the universe. This theoretical Big Rip is not caused by the cosmological constant, which corresponds to a constant dark energy density. Instead, the Big Rip would be due to a theoretical type of dark energy called phantom energy, whose energy density grows over time and eventually overpowers all other forces. But this Big Rip is only a mathematical model, and not much evidence supports it. The cosmological constant is currently the form of dark energy most accepted by the mainstream scientific community. I'll talk more about the cosmological constant and dark energy densities in the next 2 videos. One other topic I'll cover is the concept of cosmological horizons. We already know that the local speed of light is always equal to c everywhere in space-time. This is the founding idea behind special relativity, and it acts as a universal speed limit for all matter and radiation in the universe. But the universe's scale factor, A of t, does not have any kind of speed limit, and the universe can expand faster than a rate of c. The fact that light has a fixed speed through spacetime, but spacetime itself can expand at any rate, leads to some interesting mathematical surfaces called cosmological horizons. There are 3 cosmological horizons that I'll talk about: the Hubble horizon, the event horizon, and the particle horizon. The Hubble horizon is the boundary beyond which galaxies are traveling away from Earth faster than light. In an expanding universe, galaxies that are farther away from us travel away from us faster. The velocities of these galaxies are described by the Hubble constant, which says that for every megaparsec of distance, a galaxy will travel away from us by an additional 68 kilometers per second. So at 1 megaparsec away, a galaxy travels 68 kilometers per second away from us. At 2 megaparsecs away, a galaxy travels 136 kilometers per second away from us. As we look farther away, there will eventually be a galaxy traveling away from us at the speed of light. And this marks the location of the Hubble horizon. Galaxies beyond this point travel away from us faster than light. The local speed of light is still constrained to be c, but when measuring the proper distance between 2 separate galaxies, it's possible for this distance to increase at a rate faster than c. The current Hubble horizon is given by c divided by the current value of the Hubble constant. The Hubble constant actually varies with time and should really be called the Hubble parameter h of t. Another horizon is the cosmic event horizon. This denotes the maximum comoving distance r a light beam emitted from Earth can travel. In a static universe, light emitted from Earth can travel infinitely far away to any part of the universe. But in an expanding universe, there can be galaxies that light emitted from Earth will never reach. The boundary separating regions where light from Earth can and cannot reach is the cosmic event horizon. This effect also works in reverse, so galaxies on the other side of the cosmic event horizon can never send light that will reach Earth. To calculate the cosmic event horizon distance, we can take the geodesic formula for a light beam and integrate it to get the comoving distance r that light travels in some amount of time. To get the size of the event horizon, we calculate how far light will be able to travel from the present time until the infinite future. Now, depending on how fast a of t changes, this integral could result in an infinite value. This means there is no cosmic event horizon, and light can reach any point in the universe. But if a of t expands fast enough, this integral will converge to a finite value, setting a definite boundary on how far a light beam can causally affect something. To convert the comoving distance r to a proper length, we just multiply by the scale factor a of t. If the Hubble parameter were to be truly constant for all time, then the Hubble horizon and event horizon are the same, because anything outside the Hubble horizon is traveling away from Earth faster than light, and so light emitted from Earth will never catch up to it. But if the Hubble parameter is changing, the 2 horizons become separate. Current models show that the Hubble parameter is currently decreasing, which means the Hubble horizon is growing over time. So there is a gap just outside the Hubble horizon where light from Earth can reach, because the Hubble horizon will eventually cross over it. The Friedmann equations predict that, in the far future, the Hubble parameter will approach a constant value, causing the Hubble horizon and event horizon to approach each other and eventually become the same. It's also worth noting that the event horizon, when measuring in the comoving coordinate distance, is shrinking. So over time, there will be fewer and fewer galaxies we can causally interact with using light beams. This is because mathematically, this integral will get smaller and smaller as the t now lower bound increases. The last horizon is the particle horizon, whose radius is the distance a light beam has traveled since the beginning of the universe. Observing from Earth, galaxies within the particle horizon have emitted light that has reached Earth, and so they are visible to us. We say this region inside the particle horizon is the observable universe. The light from galaxies outside the particle horizon has not reached us, and so we can't see them. This region is the unobservable universe. The formula for calculating the particle horizon is similar to the formula for calculating the cosmic event horizon, involving an integral for the comoving distance that light has traveled. But we set the limits of integration from t equals 0 at the beginning of the universe to the present time. And again, if we want to convert to proper length, we just multiply by the scaling factor a of t. In terms of the comoving coordinate distance, the particle horizon is always getting bigger, because the longer we wait, the deeper into space we can see, because light from distant galaxies has had more time to reach us. Mathematically, this is because this integral will get larger and larger as the t now upper bound increases. So we have formulas for the 3 different cosmological horizons. I've left some links in the description for computing these, but we get that the Hubble horizon is about 14 gigalight years, the event horizon is about 16 gigalight years, and the particle horizon is about 45 gigalight years. So to summarize this video, we found that in FLRW coordinates, the time coordinate curves are time-like geodesics, meaning massive particles will travel along these coordinate lines as the universe expands or contracts. The spatial FLRW coordinates, r, theta, and phi, are effectively expanding along with the universe, so that 2 free particles following time coordinate curve geodesics will maintain constant space coordinates for all time. This is why we call them comoving coordinates. But remember, the proper length between these 2 particles will change over time due to the conversion factor in the metric. We also learned that the wavelengths of light will expand and contract along with the universe, meaning that light in an expanding universe will get redshifted, and light in a contracting universe will get blue shifted. This also assumes we're measuring the frequencies of light in the cosmic rest frame, which is the frame that travels along with the time coordinate curves. Finally, we talked about how the universe expansion rate has no speed limit, and we used this idea to define the particle horizon, event horizon, and Hubble horizon for the universe. In the next video, we'll talk more about the cosmic rest frame and how matter and energy in the universe can be modeled as a perfect fluid, with an equation of state involving the W factor.